Hello, my name is Vijay Jasankar and my roll number is IMT2019525. And in this video, let's look at the code walkthrough and some of the sample videos of our data visualization assignment 1. So let's get started. So this is the README file, and this file contains all the instructions with regards to installation, customization, generating the plots and the videos, and also if you want to make a new sample of the input data. So now let's look at each of the files one by one. So all of the main Python files are in this scripts directory. So let's first look at data helpers, which consists of things like get date from path, get index from path, and more importantly, it parses the file name, so which is used in data loaders. So we followed a very strict object-oriented hierarchy. So there's a base class for data loader, and each experiment builds upon it. So for example, C surface salinity or SSS builds upon data loader and implements these methods. So we have bad flags in the data, and that is loaded here. And we also can get the features out by calling this get lat long dict. And then this also extends to the SST loader and the other scalar fields. We also have a zonal and meridional loaders, which will be used very soon. And before I continue, maybe I'd also like to say that there is a custom exceptions class called data loader exception, and this is used everywhere throughout the project, and it can also push its outputs to a log file. In our case, errors.log. As you can see, it has been populated with some other things already. The real meat and potatoes of this project is in this file, the features extractor file, which will take in the get lat long dict output and will generate a plot from that. So you can see there's a base class here, and let's look at one of the derived classes again, C surface salinity feature extractor. So what this does is it first looks for that lat long dict in what is called the input dictionary. So this the way this is customized is, let's say you want to have a different kind of input in the future or something that's mandatory, and you can basically mandate that by putting it in the input dict, as we will see a little later. Um, this is the main method called get arrays and metrics, and so this creates the latitude longitude array, the matrix of that, and then the transpose, and it returns it out, which is then called here in the generate and save plot. So you can see here there are a lot of parameters like the save file and the title, and also something that's very interesting, which will come very soon, which is this config. So this config is essentially a config parser which parses all kinds of initialization and configuration files. In our case, we are loading them from one of these two files, the presets files. So as you can see, this is one of the presets, preset one, and we have three moving parts of each scalar field and about one, two, three, four, five, eight moving parts for the vector fields, and we can change them over here, and this will change the plots. This is not the only thing we can change about the plots. If you want to alter the file directly, you can also change a lot more things. All of the details of changes has been given in the README, but we read them out from here, and we create the map. So we can see we've created a base map, then we created the mesh grid of longitude and latitude and passed that over here, and the matrix transpose from the previous function. And in the report, we have indicated that there are two experiments. One is the constant experiment of levels, so we kept an integer here, and this is the other one. The reason 18 and 41 were chosen is the minimum maximum values of this particular attribute plus or minus around 5% for robustness. This then generates the X labels, Y labels in the title, and it saves the whatever figure generated into the save file provided. This goes very similar for SST and SSHA. The idea is, if at all we want to change the methods in the future, it's very simple, and we do not need to change in a lot of places. The footprint of our software engineering is not that much. Next, of course, we have our zonal and meridional, which is over here. And as you can see, this is a little bit more complex because there are two components. Um, Now, there is a magnitude matrix, which I read on the internet that it is helpful to plot it, although I haven't used it here, but this is part of the extendability of our project. Then we'll have again another projection using our same config files. We have a base map, and then we draw a quiver plot with the color, scale, width, and all of that coming from our ini files, initialization files, and we also have a quiver key which we can then configure, and we save it. Now, some of the arrows are looking quite cluttered, so I took the liberty of skipping a fraction of the values. Like I tried skipping half of the values and then quarter of the values to get somewhat more stable output. But the general method is as follows. Now, how did we get the data? That comes from the experiments folder, more specifically file choice.py. So what this basically does is takes one of these input folders, deletes the PNG, and then looks at when the tsunami was based on current data. And we can see that each file has an index, right? So this is 001, 002, and so on. And so we calculate the approximate index for the tsunami, which in this case is 73, is actually 2 days after the 73rd file's week. And now based on that index, we calculate the absolute difference of the index of any given file and the tsunami file, and we threshold that at 50. So if the difference is less than or equal to 50, we add that file to the list of files we want to do. And if it's greater, we store them separately and add half of them. So it's like a kind of linear decay function of sorts. Now, after we've done that, we then create the videos out of the visualizations, and we create the visualizations, by the way, by calling the function straight away. So, for example, we take the base path through the experiment we have, and we create all the dates and we sort them out. And once we've done that, we create a data loader, and then we create the features on the data loader, and then we call the generate and save plots. So this is the same for approximately all of these fields. In the vector fields, of course, there is a little bit of a difference because we have to create two data loaders and then merge those in the end into one input dictionary. But otherwise, it is the same. Now, once we've created that, we then want to create the videos out of that. And for that, luckily, we have something called video helpers. This is another method that I have used in a previous club to create videos out of images. So we use something known as MoviePy, which is really good. And when I created the videos first, I realized that 10 FPS might be a little too much. And so I resampled the videos by calling FFmpeg. Now, once the video helpers are done, we can then generate the videos by calling this function generate and resample if we have to. So in scalar videos.py, this is for the first experiment. We specify the input path and the output file, and the file was then generated, which I then moved into the videos directory. So you can see that there are two kinds of folders in the video directory. One is for constant tables and one is for spaced out experiment. That concludes the code review of this assignment, and let's move on now to the videos themselves. And let's look at the generated videos. So let's start with the salinity video. Just a quick note, this is the video before resampling for showing the entire progression. So you can see how the color map has changed and how the sea gets slightly saltier after the earthquake. And we have a before and after picture in the report as well for your reference. Now let's move on to the temperature. So this color map is a more of an orangish tinge because temperature is typically seen as being red. So for higher comprehensibility by the audience, we have chosen this color scheme. And you can actually see a lot more drastic change as compared to the previous one here, particularly at the bottom part where it becomes a lot colder after the tsunami. And more detailed changes have been given in the report as well. Then in the last scalar visualization, we have sea surface height anomaly. So this color map is very interesting. As you can see, there is a little bit of a blue tinge and a little bit of a red tinge. This is a diverging color map because as you can tell from the data, there are positive values and there are also negative values over here. And you can see that after the earthquake, we have a remarkable change in not just the value but also the sign of this height anomaly. Typically, we see a lot more reddish hues after the earthquake as compared to before in certain patches and certain parts. And we also see a lot more density of the blue in certain other parts before the earthquake uh, and the subsequent tsunami that happened. So a lot more detailed changes about this have been given in the report as well. Last but not the least, let's look at the currents. So you can see the red arrows indicate where the currents are, and this is for the zonal and meridional currents. And you can see that the density has changed in certain areas. So it was a lot thicker here, become thinner, and also the directions also do change post the monsoon. And for a much clearer picture, please check the report where we have included a detailed description of all the changes made. So that concludes this demo. Thank you so much for watching.